Okay, anyway, all right, with that, so remember last time, I'm going to do a quick review of the WKB approximation, something that physicists are just deeply obsessed with, and to a degree that's kind of disturbing. What I like about it is recall that we're going to set up the Schrodinger equation and just assume that the answer looks like this. Just assume this. Now, one thing that's kind of important to note about this is what's good is that you see a wave, right? So EVIX is a wave. The other thing, so it always emphasizes the wave of wave mechanics. The other thing is that this allows us to simplify the Schrodinger equation, which may mean that it's easier to solve. And what we got was, let me go ahead and just write that down. And I'll use more explicit calc language. The derivative, the square of the derivative, not the double derivative. Don't get confused about that. Here's the double derivative is equal to what we're going to call momentum squared, where P of x is 2m energy minus the potential. And again, the potential is no longer, not necessarily, oh, that's it. Sorry, P squared. P squared is that. Okay. And energy minus potential is kinetic energy, and P squared over 2m is kinetic energy. All right, so all this makes sense. And I also want to point out this is not an approximation at this point. And one of the reasons that you might want to work with expressions of this form is that as a partial derivative, partial equation, sometimes if you just manipulate them, just do a little algebra, all of a sudden they're like easy to solve, whereas before in the original, like as a Schrodinger equation, given a potential energy, maybe it's like impossible to solve. So that's the value of this. And again, there's no approximations. Now you may seem like you've pigeonholed yourself into a wave function. So there's an approximation made here. Actually, there isn't. Now let me trick you into thinking that what I just said is not true. I know that there are example problems, and just forget this for now. This isn't, I don't want you writing this down in all honesty. I'm just kind of speaking out loud, thinking out loud. Okay, there are example problems where the solution is just x. It happens, like certain potential surfaces, that's the solution. Okay, so does that mean that I can't solve that, given this form? Right, so I'm telling you that there's no approximations at this point. Yet, how can certain problems have this when I'm making it that? Right, it seems like, well, no, there has to be, I've limited the answer, therefore there's an approximation. Does that sound right? Given that I just said that's not true, you should be doing. Okay, can anyone resolve that? How can I still work with the model problem where this is the solution, normalization, whatever. Anyway, it's x. How can that be true and this be true at the same time? And I'm telling you there's no approximation. So I should be able to get an x out of this. How can I do that?
Natural log.
Yeah, the s is just a natural log of x. Even the natural log of x is x. Right. So again, what I'm pointing out is that there's no approximation. Now remember that also, all right, let's forget this. We've been doing a lot with e to the kx, and what you're seeing is s is simply responding to the potential surface. So again, that's just what I like about this is that it gets you to understand what's the underlying of quantum mechanics, its foundations, and that is that the momentum affects the wave function, and the momentum is responsive to the potential surface when the potential surface is curving. And this is a way to do that. Okay, now, last thing we did is if v of x is just V naught. Now that's again our flat surface. I'm going to cheat a little bit. Now we have done enough, we did Diffie-Q, right? Remember I showed you how to solve the Schrodinger equation in the case of no potential, and we found that the wave function is e to the I kx. Okay, so that means that the S, okay, so therefore S would be what? I kx, so it has to be h bar kx, right? So again, if we have a flat surface, and I know that because I actually already solved it, so in a way I'm cheating. Okay, in that case, the double derivative is what? Huh?
Zero.
Yeah, 0. I'm just trying to wake you people up. Okay. And then what you get, and let's see, what else we get? We get P squared is just 2me, which is just h bar squared k squared. Right, because you know, and again, if you're confused with that, remember that k is 2. I hope you're just like sick of seeing this. 2me over h bar squared. H bar. Yeah, thanks. It's squared when it's inside anyway. All right, so all this makes sense, and do what you end up with. Now again, a lot of what I wrote is cheating. It's going to be plus, I'm just taking the square root, plus or minus, that'd just be h bar k. So I just took the square root of h bar squared k squared, and don't forget plus minus, that's the thing. In which case, when you integrate the integral s of x, the integral of s of x is s of x, which is equal to the integral plus minus, sorry Mike, why am I doing this? What the hell is wrong with me? I thought I could write this out quickly. That's equal to plus minus the integral h bar k dx, and of course that's just 8 plus or minus, God, what is wrong with me? Sorry. I probably needed to read my notes a little bit more before class, so I'm a little fluency. And then, therefore, the wave function is e to the plus or minus I over h bar kx, which is e plus or minus I kx. Okay. So anyway, now I just wanted to show you that everything's fine. There's no approximation. But now I'm going to do one. Now I'm going to make an approximation. Let's see here. Okay, now, all right, so now we have to say if, oh, where am I at my notes? Sorry, turned to the wrong page. Okay. So just remember, in your notes, not constant. In your notes, just understand I was doing an approximation. Something we've already done, so I don't really want to do that. I want to now talk about a potential surface that actually got some curvature to it. This is a stupid thing to do because I've already solved it, right? Cool that it works. Okay, anyway. All right, what you do is you're going to make an expansion in the function, this momentum function, essentially, let's just call it that. And remember, I told you that you can technically make expansions. It's like a Taylor expansion, right? But I'm doing it instead of like x, I'm using a constant. And I know that's really kind of weird and uncomfortable. It actually makes me uncomfortable. But I mean, given that I haven't really defined what s, and these are all functions. S0 is a function, S1 is a function. They're all functions. And S1, S2, S3, it goes on forever. Sure, I mean, if I have infinite flexibility to making these whatever I want them to be, then of course I can describe any function. If you give me infinite flexibility to write a function, I can write any function. I mean, that's, I think a middle schooler would understand that. So that's what I've done at this point. It just looks weird. It's like I'm comfortable to see an expansion not in the variable, but it's fine. Okay, now what we do is plug into the above at the very top. So, it's going to drive me crazy unless I make sure that equation 1. So plug into equation 1. Okay, what do you get? Into 1. You get, okay, this is going to be, I'm going to use my little dash there for a derivative because there's so freaking many that it's going to drive me crazy if I don't. And I'm just going to write out to h squared 2 prime. Okay, and I'm going to put dash, 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 and I'm really going to stop there. Okay, there's the single derivative squared. Now subtract I h bar. Let's do the double derivative. S naught double derivative. And here's a hint, by the way. We're only going to solve for S0 and S1. And that's how we're starting to make approximations. H bar, S1, double derivative, next. And I'll go to h squared just because I did so on the other side. And this is equal to P, our momentum function squared. Okay, so what? Okay, now this is another mathematical trick that you'll see frequently. We're going to collect like terms. We're going to collect all the terms that don't have h bar in it, and the ones that do have h bar, and the ones that have h bar squared. Actually, I won't go that far. I'll just stop at h bar. And this is, people sometimes, if you Google WKB approximation, there's a couple of good references that describe this derivation. I've taken them and I filled in some of the gaps, by the way. That's how I came up with these lecture notes. They'll often describe this as perturbation theory. Kind of. That perturbation theory has a very strict definition, and this definitely is not formally what we call perturbation theory, but it's perturbation theory-like. When we do perturbation theory, which is an approximation to solving the Schrodinger equation, we do something really similar. So that's why people say that, but it's not really perturbation theory. Anyway, okay, now what I'm going to do, and I hate doing this to you, I try never to do this, but I'm going to do it anyway. I'm going to subtract this and set it equal to 0. And the reason I do that is, let me collect the h to the 0 terms. Okay, so here's the square of the first derivative of our odd Taylor-like expansion. Okay, now the reason I brought over the p squared is because it also does not have h bar in it. So I'm putting these brackets in, but they're all part of this sum. So I'm writing out a single expression, by the way, but I'm using these brackets not as mathematical tools, but as visual tools. Now, another thing is, I don't want to work through the bloody algebra, but you see that there's a square. So there's cross terms. And I'm trusting that your algebra is up to speed. Okay. So here is the h0 term, h to the 0, which is 1. Here's the h to the 1 term, and then I have h squared terms. And again, I'm not doing the algebra. I'm not gonna FOIL this out and combine it here because that's just algebra, and I hope you and I'm fine if you don't do it either. Cool if you want to spend some time on algebra, but you would get to this. I sat down and verified that was the case, but I don't want to spend an extra 10 minutes doing that in class. Okay, now one damn thing about this is that it turns out the way that we group these in units of h bar. Each one has to be 0 for the whole thing to be equal to 0. So and I'm not entirely sure why. I think it has to do, I mean, I know why that, remember we covered separability. So what I'm doing is I'm invoking a separability type of argument where like all the partials with x are their own ODE, and then all the partials with y are their own ordinary differential equation, and on and on and on. So we covered that in the first week of class. I'm not entirely sure why every power of h bar has to be equal to 0. Actually, you know why? You know why that might be? Is because if each term fundamentally has different units, then, because this has no h units, this is h units, 0 has no units. The only way that's going to work is if the terms in brackets are 0. So I think that might be, that's my best guess at a reason why that might be the case. Okay, so anyway, so let's assume that I'm right about that. It is true that each one is 0. So if you set this to 0, we'll set this to 0 in a little bit. This guy is giving us a simple equation. So I'm going to write out I'm writing it out now at this point, is equal to, the square of this is equal to p squared, so I'm just going to go ahead and do take the square root. There you go. And therefore, S naught is just the integral, plus or minus, plus minus the integral of p of x. Okay, using the same mathematics I had used before of bringing the partial of x over to the right, integrating the partial, which is just the function, and yeah, there you go. So again, this is identical to what I did, and I hope your mathematics is okay with that. I just kind of did it, did not. Okay, now let's look at the other guy. So that's what we get from here. Now let's look at this one. If we look at this one, I got 2. Let me use my, I know I'm jumping around between ddx and a partial. I hope that doesn't bother me too much. Now, of course, that's going to be equal to I double derivative of the first function. Okay, now the funky thing is that, of course, I know, I happen to know what this is. This is plus or minus the momentum function, just e minus v. Right. So I've got that. I kind of hate to leave this. That's kind of neat. Let's see here. Okay. So let me just keep working downward. Okay, from here, I'll just write it. Well, now I'll write it down again. That's not prime. That's one prime. That's not double prime. Okay. So what you get from this is I'm going to divide by 2 and S naught prime. So again, I try not to ever overwrite my own stuff. But what I've got is, if I substitute in what I know the derivative of the first term to be, if I were to remember that right up here, I know that S naught is plus or minus p of x. Then the derivative of that, the derivative of the derivative is the double derivative. If that's the derivative, then the double derivative, the plus or minus is still, the derivatives don't change plus or minus, right? Okay, now the cool thing is that the plus and minus actually cancel. I always thought that was kind of neat. So anyway, that's like this cool, clever trick. All right, what's the derivative of a function over the function? Remember the identity for that? And it is, even when I don't look at math in a while, I know that one immediately. This is something like I'm sure when I'm 90 I'll forget, but not now. Derivative of the function. Remember that we used that to solve the boundary conditions of the flat potentials? The thing I kept kind of screwing up? Oh, the log derivative? What's the integral of 1 over x is what?
Log of x.
It's the log. Right, so what you can say, right, so you can say that this is the derivative, and so that you don't get blown away by this. I'll be a little bit more careful in my mathematical notation. Okay, so the derivative over the function is the derivative of the log of the function. Right, so that works for x and any function of x. I'm sure that's a very easy proof. Okay. All right, now, here's the thing. We're basically done. Watch this. This is neat. Okay. So the wave function is e to the I over h bar f of x. Now remember that now I'm going to expand this to s0 plus h bar s1 and blah, 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 blah. Okay. So e to the I over h bar s0 of x, which we know is plus or minus the integral plus h bar s1 of x. Okay, let's see. What do we got? So we got e to the I over h bar s0 of x times e. So remember that we have e to the a plus b, it's e to the a times e to the b. Again, I'm hoping that you're caught up enough that I'm not throwing you off. Okay, so I over h bar, okay, so the h bars are gone, right? Because again, remember we expanded this, so that I got a little lost there. It's like, where's the h bar? I over 2 I times, sorry. There's the I, and there's an I, so I have an I over 2. Yeah. Wait. Sorry, God, sorry folks, I'm I did something stupid. If this is I over 2, change in the derivative of ln, then what you do is you integrate both sides. Sorry, I forgot to tell you what the function is. I noticed I was about to write it down, and it's actually, you see why I got confused? Because there's nothing to it. If the derivatives are equal to each other, you can just integrate both of them. So the reason I got a little confused here is like all of a sudden I'm writing down the function, and I was like, wait a minute, I don't think I can find the function. So sorry about that. God, that's an excessively large number of brackets. And again, we're going to just leave off, times e to the h squared term. Let's just leave it off. Yeah. All right, so, at this point, we're definitely making approximations because I'm leaving off the higher order terms. Okay, now, question?
Ideally, we are trying to find the wave function, right?
Yeah, this is it.
So, are we done now? Or?
No, one more step. Yeah, we are done. Let me just insert S naught, which is the integral of the momentum. And then we'll do a couple of examples. Actually, mostly we're going to solve the energy. Okay, so this ends up being E I over h bar Now, remember that I've actually already defined this function as the integral of the momentum deal. God damn it, did I do that again? Plus or minus, right? What is, I keep forgetting plus minus. I don't know why, I just absolutely do not, it's like I'm like opposed to doing it for some reason. There we go. Let's write this out briefly. Okay. Now the other guy is, okay, so I've got a minus, I've got a minus half natural log of p of x. Okay, now, can anyone simplify that? Let me do an aside, so these are my asides. Minus 1/2 ln of x is ln of what? See, what I'm trying to do is I'm trying to get the natural log. I'm trying to get the natural log out front. I want e to a natural log because then I just get rid of the e in the natural log, right? It's like way better.
I want x to the power of minus 1.
Yeah. And again, on an exam, I'd make sure you have these identities. I mean, I'm kind of hoping that you just have these in your head, but if not, in an exam, not a big deal. You know, when I was like writing my notes, I always look these up before I put them down here, just to make sure. Okay, so what you end up with then is, hopefully it's just kind of obvious. I'm just going to write it down. I'm kind of switching the order here. So yeah, I try not to do these things. So I put this here. I try not to do that, by the way. I know just even a little thinking can throw you off. But anyway, that's, God, what the? I just want to make typos today. Kind of started out a good day, but today's going downhill rapidly. Anyway, yeah, there you go. So. That's the wave function. That's the WKB wave function. Now, technically, it's a semi-classical wave function, and one reason that is that we truncated out higher orders of h bar. In fact, we largely, this is largely here. This is the most of the wave function, right? And this is the h bar to the 0th term. So. Sometimes you'll see that this is called an approximation where h bar goes to 0. And I don't think that's accurate because there's an h bar there. But anyway, the point is that an approximation is made to the solution. It's based on h bar. We kept the terms that have h bar to the 0 on it, so that's why I think people say that. It is an approximation, and it does work really well for. Here's the thing, the reason that physicists really love this guy is that occasionally you write down a Hamiltonian that cannot be solved. Maybe you can do it on a computer. Generally you can always solve these, but there are certain mathematical problems that it's known that there is no, what we call an analytic solution. That means e to the x, e to the f of x. It is known to be impossible to write it out that way, based on the nature of the problem, the Hamiltonian. That's always the problem. It turns out the WKB can sometimes solve those, although obviously approximately. So that's why physicists love this, especially for nuclear decay. This is one of those problems they had no solution for, but this is the best anyone could do. So they're kind of obsessed with that. Now we can also solve wave functions. And actually, I'm not going to do so much of that. I'm actually going to solve energies. Because what you can do with this, as in on your homework, is you can solve very easily the Morse potential energy, which I had on your homework, which otherwise is hideous. I mean, hideous. But if you do this, I think that answer is actually exact, but I don't quite recall if it's exactly the right answer. Certainly it's close to it. So what do I want to see here? Okay. Now, so that's the wave function, but remember, wave functions are usually simple tools to get energies. So how do you get the energy out of it? And to do this, like in a lot of chemistry, quantum, I'm going to do example problems. We'll do particle in a box, and then we'll do harmonic oscillator, and then that's it. And next time we're going to talk about multidimensional quantum, and we'll go back to flat potentials, and we're going to solve the particle and sphere problem. And then we're actually going to start on your textbook. That's been a while since we're in. Okay, let's see here. Let me continue down here. I want to point out that when you have a plus or minus, this thing I'm desperately trying to forget, a function with plus or minus in it, it doesn't work, right? It can't be plus and minus at the same time. So the solution to that is to note that you're going to have two terms, and remember that the linearity of quantum mechanics means that you can write linear combinations of solutions. Now, what is often the case is, here, let me go here. If we use familiar language, if you want to call P of X equal to H bar K, if you do that, it's kind of nice. You actually generally see it done this way, and by done this way, what I mean is you end up with K of X. Am I going to say H bar somewhere? Okay. Yeah, I remember why that is. This always throws me off. Let me write this out, and then I'll explain something that, once you get to these higher level textbooks, there's a lot of things that don't get explained. And it's because it's like, they just expect you to be advanced along enough to understand why it looks the way it does. But what happens when you're reading it for the first time? Right? That sucks. You don't know what the hell is going on. Okay, now let me put a disclaimer on this. Let's call this the E greater than V solution. It's a little hard to know what V is if V has some functional form, but anyway. Okay, now you may notice that, where's my H bar? And here it's fine, right? So you see how I simplified it. K is our wave vector, right? In our language, momentum is H bar times K. K is a wave vector. So anyway, I kind of maybe it'd help if I got it right. Plus minus, Jesus. Anyway. So this is fine, right? And you can see why people write this out, because you don't have to write 1 over I over H bar so much. Literally, that's probably why they did it. Okay, where's my I here? I almost did a double take when I was writing it down, because I was like, wait a minute, where's my H bar?
It's in the coefficient.
Yeah, you can just put it in the coefficient. So anyway, when you read textbooks and you see stuff like that, you're like, well, wait a minute, what the heck? That's what's going on. Anyway, so heads up. Okay, now if V is less than the energy, then you often will see, you'll often see this. Kappa, and I'm trying to write this. You notice that I did not write an H bar. And I know that you may be like, wait a minute, which one's plus, which one's minus, it doesn't matter. Integral kappa. Okay, and this is for E less than V, where kappa is 2m V minus E over each bar. Okay. Anyway, so, what do I want to say? Okay, there's a couple of things we can get from wave functions from this. So again, I know we've really gone down a math rabbit hole, but I do want to point out that, again, the big picture is that you can think of waves as being, these are the ultimate correct descriptions of quantum mechanical things. by quantum mechanical things, I always mean electrons. And the nature of potential surfaces is to simply change their wavelength in a spatially varying way. And if you get that, then you've done pretty well. Let me point out something else. A couple other things that you tend to see with in quantum mechanics. So let's just say that B is 0 because it just is, whatever. There's a lot made of the fact that these guys are they're EUBI. Technically, when you see this, it's often called a phase factor. That's the language of that. Okay, so wave functions are basically an amplitude divided by the momentum. Okay, and if you then know that,
It's a probability, right?
huh?
So the probability is inversely proportional to the wave number, right?
Yeah, what? Sorry?
We got the probability density, right? Pi square.
Yeah.
That inversely proportional to the.
Amplitude, forget this, it just doesn't matter. Yeah, I'm not worried about that. This will cancel out. Right. So, and then don't forget that really K is P. So you can say that that's H bar A amplitude, the absolute value of the amplitude over P of X, which well, not sort of, is equal. Remember that P is the momentum. And so mass times velocity. And of course mass, we won't assume mass changes with velocity, although it does. But this is a relativity class, although I know I brought that up. Okay, the point here is to point out that, let's do like a harmonic oscillator, because it's on your homework. When you look at that problem, and of course, huh?
There will not be H bar, right? So the
So K.
so we need to change the K of X, the momentum at number 2.
Wait.
The P of X is K, H bar P of X.
Wait, Jesus. Right?
Yeah.
So I said K, sorry. H bar K of X. So I said K is P over H bar.
And so, but we already had P of X, so you didn't use that and you used K of X.
Hold on. All right, so
we don't need the H bar anymore.
yeah, it doesn't. Well, look, it's all. I'm playing games with the coefficient. So
yeah, actually the function is the wave function is 1 over root of P of X, right?
Okay, yeah, right. So I know. So the problem is that I'm being loosey-goosey, right? So recall that that's the solution for certain. Given the approximation. I then called it H bar K of X. I did that because whenever I look online, this is almost universally how I see it. And notice that the P suddenly just became a K. So where's the H bar? The H bar got eaten into the A.
Okay.
Right. So not a big deal. And I know it's awkward, and there's really no good way to do this. It's just that this is almost universally how you see it. And so I want you to know where that comes from. But when it comes back to this, I'm bringing it back. And I know it's really awkward. It's really awkward, but it's kind of confusing where the H bars are, right? Yeah. All right, now, the point here is to show that the amplitude, the wave function squared is proportional to 1 over the velocity. 1 over momentum, but momentum's velocity. Now, where that manifests itself quite frequently in wave functions is let's take a high energy guy. So not the lowest energy, but a real high energy of a vibrational wave function, right? It would look like that. A bunch of nodes, right? So I just drew a wave function with a bunch of nodes. Notice that we often call these areas at the extremities, we call those classical turning points. When spring is stretched to its max. It has it has energy by virtue of having temperature is one of the things that cause things to vibrate. You know, you have to be really hot, but so it has some energy, and that kinetic energy is converted to potential energy if it stretches to a certain point. Now, technically, if all the kinetic energy is potential energy, it needs to have stopped. If it stopped, then you've got a singularity. Now, the point is, now this is actually a mistake. In terms of the approximations made, I have a singularity here. Because you notice that you say, oh, well, A is 0. A is not 0. That's one of the problems. When the way this is written, A cannot be 0. So you actually have a singularity here. That's actually, that's the biggest mistake of this approximation, is that there's singularities. And the way around that is deeply complicated. I'm going to talk a little bit more about that next time. The point is that that's why you see wave functions bunch up in low kinetic energy regions. This kind of behavior. Now again, so one of the points of this is, if we solve the harmonic oscillator wave functions and plot the wave function squared, this is what you get. And if you understand it at that level, okay, great, but that's not very deep. When you do this kind of thing, you can see that an analysis of why it comes out this way, again, this is the solution with no approximation, is that the particle is spending more time here at the endpoints. So, and that also is one of the few times it actually makes sense. That if the thing is bouncing back and forth, it's spending a lot of time moving, but when it's stretching and then coming back, it's actually slowed down, so it's more likely to be in this expanded state, expanded or compressed. Don't forget that about vibrational potentials. That's technically expanded, that's compressed. So that's where it spends all its time. So anyway, that's just a thing that you get out of this. The last bit I had just enough time to do, I will about time, maybe I'll just set this up, is energy, the energies of these things. We can do particle in a box, particle in an infinite box. And I'm going to do something that's a little crappy. I'm going to define the box differently. I'm going to say the box is from 0 to A. Now, before it was from minus A to A. Now it's 0 to... do I want to do A or do I want to use the letter L? I might want to use the... I want to use the letter L, sorry, because I don't want it to look like the other problem. And of course, the wave functions look like this, just like last time. Now, the dangerous thing is, when you do it this way, it's actually easier to solve. This is how I do it for my undergrads. The way I showed you is actually a little harder. And I did that on purpose because, again, it's grad school. And you can solve this complex, or you can just figure out that the wave functions. Here's why it's easier. You don't run into even and odd. Everything is a sign. 2 over L sine n pi x over L. I had this memorized at this point in my life. So anyway. Okay, now, I just wanted to point that out. Now when it comes to this guy, to our WKB, it turns out that A, let's go here, up there. A's got to be equal to minus B. Now, for one, that gives us a sine function. So it's like, well, no duh, but you know the wave function has to be a sine function. But there's actually another reason. A is a right wave and B is a left wave. If it doesn't spend just as much time moving right as it does left, it gets out the box. It can't get out the box. So A is equal to minus B. That's just a nice hand-wavy way to solve that. It actually can be done mathematically. We can figure out A and B mathematically using boundary conditions. And I was kind of torn whether I should do it this way, or centered on minus A to A. It actually is slightly harder to do it the minus A to A way. It's a little bit easier to do it this way, but I wanted to push you a little bit. Okay, so if the wave function is 1 over the square root, the momentum vector sine the integral of the said vector So I've just taken e to the integral plus e to the minus integral, minus e to the minus integral, and I said that's a sine function. You know that this has got to be equal to n pi this has got to be equal to n pi to satisfy the wave function at 0 and L. That's just the wave function at 0 and L. It has to equal to n pi, n equals 1, 2, 1, 3, for the side, for all the sides. Side of 0 or L to equal 0. Okay. Anyway, and so I'll stop here. I just want to point out so that what that means is that the integral of kx from 0 to L. I notice I never defined the limits of the integral. I never defined the limits of the integral. It's the limits over which, it's usually minus infinity to infinity. This guy ends up being easier because the box is only defined between 0 and 1. So anyway, now we'll start here, but what I'll show is, and again, you could probably do this yourself, what you end up with is that based on the definition of K as E over, the definition of K, what you get is this, which is, of course, the exact answer for the particle in the box. One reason that works is, remember that the double derivative for flat potentials of our S function is 0. All subsequent higher derivatives are 0. And the WKB approximation is not an approximation for flat potentials. So all that expansion in h bar is exact when the higher order derivatives are 0. So I needed to get the exact answer, and I did. I'll do this next time because I'm holding you late, so you need to run. So anyway, next time I'll start here reviewing, and that should also set you up for your homework. And then we're going to go to multi-dimensional.